Science, a world of surprising facts and incredible wonders. Stay tuned as we travel through the exciting, unending world of scientific phenomena.
Oh, no, not another science show.
Yes, it's not another science show. This week's episode, Heavy Metal.
Can you imagine what the world would be like without metal? It's everywhere. We drive around in contraptions made out of it, and when we get where we're going, there's still metal. Steel roofs and nails and steel support beams.
Even the mirror that you look into every morning has metal in it. This week on Not Another Science Show, we're going to be looking at metals, what they are, and how we can forge them into materials that we can use. Stringer, do you know how to make steel from iron?
Sherlock Holmes told me. Elementary.
Elementary? No, seriously, Stringer. Do you know how to make some of the world's strongest metals into a fine thread?
Elementary.
Oh, elementary you. One more try. Tell me why metal corrodes.
Same answer. Element 3.
Oh, I get it. Elements. Basic chemistry.
Not a very good one. How about this one? Suppose with the harbor down here and the island airport over there, we have float some and jet some. You wouldn't harbor any resentment against me for that joke, would you?
I certainly would. Your
No, how
puns
about
are
that?
getting worse and worse.
Everything on Earth is made of basic elements. Sometimes those elements are found in their pure state, like hydrogen, and often they're found combined into compounds, like this lake full of hydrogen and oxygen. All 103 known elements can be mixed and matched to combine into various compounds, except for 6 of them. They're called the inert gases, and they don't easily combine with other elements. They're sort of the snobs of chemistry. The ancient Greeks used to believe that there were only 4 elements: earth, air, fire, and water. That theory held for many centuries until modern chemists discovered that earth, air, and water were compounds formed from different elements, and that fire was a chemical reaction.
It was a Greek, Democritus, that came up with the idea of the atom. The story goes he was watching some fish swim in a pond. He reasoned that water consisted of separate particles with spaces in between. He figured that the fish were completely surrounded by these particles. He extended this assumption to birds flying through the air and roots of plants growing through the soil. For centuries, it was thought that the atom was the smallest thing on Earth, but then it was discovered that the atom consisted of even smaller particles: protons, neutrons, and electrons. The protons and neutrons are found in the middle of the atom. It's called the nucleus. The electrons orbit around the nucleus. It's the position and number of each of these particles that determines the characteristics of each atom. These characteristics occur in nature in a very orderly fashion. So orderly, in fact, that it was possible to predict the existence of new elements that were not yet discovered. This chart, called the periodic table, puts together elements that react in a similar manner. They're listed in vertical columns called groups. The group at the left is the most reactive. As you move toward the right, they become more and more stable. The inert gases are found at the furthest column to the right. The elements are also assigned numbers. The atomic number represents the number of electrons in the atom. The atomic weight is the number of protons and neutrons. As you move toward the right, each heavier atom has one more proton.
When you're dealing with atoms, there's some basic rules. The first one has to do with the charges on the atomic particles. Electrons are negatively charged, protons are positively charged, and neutrons don't have any charge. The second rule is that in a well-balanced atom, there should be an equal number of negatively charged electrons and positively charged protons. Now, this plate can represent the orbits or shells of an atom. Actually, the orbits aren't flat like this, they're three-dimensional, but this is a lot easier to hold up in the wind. Each orbit can only hold a certain number of electrons. The innermost orbit can only hold 2. The second and third have spaces for a maximum of 8, and following orbits have their own special requirements. The orbits are filled from the inside out, so the innermost are filled first. Now, armed with the basic rules, here's what chemistry is all about, the mixing together of atoms of different elements to form compounds. This may look like a piece of styrofoam with marbles stuck in it, but in actual fact, it's a sodium atom. Sodium has 11 electrons, 2 in the innermost orbit, 8 in the second, and only 1 in the outermost orbit. Now, it's electrically balanced. It has the same number of electrons as it does protons, but it would really rather have 8 in its outermost orbit. Here's chlorine. It has 17 electrons, 2 in the innermost, 8 in the second, and 7 in the outermost orbit. It would really like to have 8 in the outermost orbit too. So when the conditions are right, sodium and chlorine get together. When sodium gives up an electron, it now has more protons than electrons and becomes positively charged. And when chlorine picks up this extra electron, it becomes negatively charged. And like the opposite poles of the magnet, they stick together and form sodium chloride. That's table salt. The chart has the elements grouped horizontally as well. Each horizontal grouping is called a period. And elements in the same period have the same number of electron shells. First period has 1 electron shell, the second period has 2 electron shells, and so on. The last element in each period is an inert gas. They're inert because their outermost shells are filled.
Not only are atoms incredibly small, but they're mostly empty space. Imagine that there's a marble sitting on second base. If we pretend that this marble is the nucleus of an atom, where do you think the outermost electron shell would be located? Some of the atom's electrons would be orbiting at the very edge of the baseball stadium, way up there in the cheap seats. But electrons don't travel in a fixed orbit like the planets in our solar system. Chemists now believe the electron can be found anywhere within its orbit at any given time.
If you've ever scraped the ice off a windshield or looked at the condensation on the inside of a window in the wintertime carefully, you've probably seen that ice is a network of crystals. A crystal is a solid with its arrangement of atoms in a regular, repeating pattern. Crystal is about the most common shape on Earth, and all metals are made up of a latticework of crystals. Crystals all start from seeds, smaller crystals. Look at these salt crystals. If you look closely, you'll see that the bigger ones look just like the smaller ones. That's because of balance. As the crystal grows layer upon layer, the way that the atoms join doesn't change. So the big crystals look just like the smaller crystals. The properties of a metal, whether it's strong or weak, what temperature it melts at, whether it's bendable, all have to do with the structure of the crystals that make it up. In lead, the crystals form a loose latticework. In steel, they're more tightly packed.
Iron is found in nature, doesn't look much like this ring. Instead, it looks a lot like this rusty bar. That's because the chemical formula for iron ore and rust is the same. Fe2O3, iron oxide. That's 2 iron atoms plus 3 oxygen atoms. To use the iron, we have to refine it. That is, get rid of the oxygen. While at the mine, the iron ore is crushed into small pieces. Powerful magnets attract the pieces with the heaviest concentration of iron ore. Water is added and then removed to concentrate the ore.
It's sort of like making mud pies. Before water is added, this soil just falls apart. After the water is added, the soil cakes and will dry as a hard lump. This process results in iron pellets that are shipped to the refinery. There, coal is baked into a substance known as coke. Ovens that get as hot as 980 degrees Celsius literally cook the impurities out of the coal. The other substance that's used to refine iron is limestone. It's not a factor in the chemical reaction. Instead, it's used to get rid of any impurities.
To make iron, layers of ore, coke, and limestone are put into a blast furnace. Once the furnace is loaded or charged, a blast of superheated air is blown through the material. The chemical reaction that creates pure iron from ore looks like this. The intense heat causes the molecules in the compounds to start vibrating. The substance gets red hot. The ore is a mixture of iron, Fe2, and oxygen, O3. Coke is 90% pure carbon, and when heated, releases carbon monoxide, that's the 3CO. So the energy from the intense heat causes the chemical bonds to be broken. The oxygen atoms are released from the iron and join the carbon monoxide molecules released from the coke to make CO2, or carbon dioxide. This process removes almost all of the impurities from the molten iron. Any impurities in the ore are separated and rise to the top of the furnace with the limestone. Limestone is porous, and when the mixture is heated, it attracts the impurities in the iron ore like a sponge as it floats up through the various layers to the surface. The slag, impurities, and limestone are saved and used in parts of the construction industry. The blast furnace is drained from the bottom to remove the molten iron.
The steel-making process starts with the molten iron from the blast furnace. This material goes to another furnace where limestone is added again. This time, pure oxygen is injected to increase the temperature and burn off any remaining impurities. As it is blown through the molten iron, any remaining carbon is burned or oxidized and forms carbon monoxide or carbon dioxide. Any other impurities which made it through the blast furnace are oxidized and float to the top along with the limestone. If this were continued too long, all the carbon would be oxidized, but so would the iron. So, at just the right moment, the oxygen is removed, leaving the iron and a small amount of carbon.
Steel is an alloy or combination of iron and carbon. The amount of carbon determines the quality and characteristics of the steel. For example, the steel used in chains and nails contains between 5/100% and 12/100% of carbon, whereas the steel in razor blades contains about 1.4% carbon. Other metals can also be added to steel to make different products. The addition of chromium produces stainless steel, a harder, tougher form of steel. It's used in cutlery. Silicon can be added to increase the steel's resiliency. It's used in springs. The characteristics of a metal comes at the atomic level. If a metal is brittle, that means the crystal pattern can be broken easily. If I add another metal with a different crystal pattern, there is more strength. Pretend that this piece of wood is a layer of steel 1 atom wide. The grain is something like the crystal pattern. It will bend, but if I apply too much force, the bonds holding the crystals together will let go. But if I add metals with different crystal patterns, I should get a different reaction to the same amount of force. I could be here all day. Other metals are refined in similar ways, but we aren't always looking for purity. The beauty of metals is that by combining them, we can come up with new compounds with just the qualities we want. For example, this wine glass is made of pewter, a combination of tin, copper, lead, or antimony. And this horn is made of brass, a combination of copper and zinc. I think it sounds swell.
All steel emerges from the furnace as a molten liquid. It It's then made into red-hot ingots, which can be transformed into many shapes and sizes. Long, narrow billets will become reinforcing rods, small diameter pipe, or can be stretched further to make wire. Thicker blooms are pounded into shape by powerful machines that create thin but strong girders and railway track. Slabs are rolled out to become sheet metal or large diameter pipe.
The problem with metals like iron and steel is that they rust. And rust is really just iron trying to get back to its roots. The atoms that make up iron aren't happy in their pure state. As a matter of fact, when iron is found in nature, it's almost always found as iron oxide. Then we refine it, we purify it into iron by removing oxygen atoms. But those oxygen atoms and that iron will try to recombine whenever they get the chance. When something combines with oxygen, it's called oxidation. Probably the most familiar form of oxidation is burning. Ooh. And rust and corrosion is really the same thing, but it happens at a slower rate. Okay, here's the trusty rust demo. I've got 5 test tubes here, and each one has got a piece of steel wool in it. The first one is filled with ordinary tap water. The second one's filled with boiled tap water. That's so it won't have any air in it. The third one has no water, just air. The fourth one has tap water, which we will turn into salt water. The fifth one gets a little bag of silica gel that came with my new camera. That'll dry out the air. Now, I'll cork them. I'm going to put corks on all of them except for the one that I want to expose to the air. Okay. Ready? Do your thing.
Thank you, Mr. Rust. After about a day or so, we find that the wool in the test tube with the boiled water and the test tube with the dry air didn't rust. That's because rust is a chemical reaction that takes both water and oxygen to happen. We can also see that the wool in the test tube with the salt water began to rust first. That's because salt speeds up the chemical reaction. That's why if salt is used on the roads in the winter, the life of a car is cut drastically. Steel manufacturers are always looking for new ways to protect steel from both water and air. The easiest way is to coat it. Thank you. Tin is not affected by water or air, so it's used to line many of the cans in which food is packed. There is a problem with tin, though. It can crack, leaving the steel underneath exposed.
There are also a variety of paints and coatings available. The main purpose of paints and coatings is to cover the metal so that it can't be exposed to the air or moisture. But metal tends to expand and contract with changes in temperature. And on something like a car, you have to expect that it's going to get a little dented. So ideally, the coating should be able to change shape along with the metal. Some rust-proofing dealers try to get around the problem by using thick layers of a synthetic tar-like substance. And car manufacturers try to get around the problem by using many layers of paint. The best paint for a metal surface is one that will get into all the little nooks and crannies of the surface crystals. But unfortunately, most paints and coatings aren't perfect. Keeps guys like you in business, huh?
Aluminum coatings are meant to be oxidized. Unlike corroded iron, the corrosion of aluminum happens only at the surface. Once the entire exposed area is oxidized, the chemical reaction stops, and the aluminum can't corrode any further. Steel coated with aluminum is used on planes and on trains. It's very strong and totally resistant to rust. Zinc is another coating applied to steel. The process is called galvanizing. If a crack occurs, the zinc corrodes rather than the steel. The process is called galvanizing because it works by galvanic action. Galvanic action occurs whenever you have two dissimilar metals in an electrolyte. Thank you very much. You hang around here a lot, don't you? An electrolyte is a liquid that supports the flow of an electric current. The two dissimilar metals in this galvanized nail are zinc and steel. The electrolyte is the moisture in the air.
Here's some galvanic action you're familiar with. It's a flashlight cell. It's a zinc can that holds an electrolyte in paste form with a graphite rod running down the center. Because the zinc has more stored up energy than the graphite, it's more anxious to corrode, and an electrical potential exists between the two. If an external connection is made between the two metals, an electric current flows. The current that's flowing actually comes from the corrosion of the zinc. As the zinc corrodes, it releases small particles of itself called ions into the electrolyte. For the action to continue, it's necessary that that external connection be present. If I remove the bulb, then the ions that are being released by the zinc have nowhere to go, and the corrosion stops. If I leave the bulb connected, eventually the zinc will corrode right through, and the cell will leak. In all galvanic cells, the direction that the current flows depends on the differences in the two metals. In this case, the zinc is acting as an anode, and the graphite rod as a cathode. And there's a hard and fast rule of galvanic cells, that anodes corrode and cathodes don't. Why, thank you. It's okay, we'll call you. Here's another cell. This time the metals are magnesium and steel wool actually. The electrolyte is plain old tap water. Magnesium is a very highly refined metal, so it's much more anxious to corrode than the steel is. But in this case, there's no current flowing because there's no external connection between the two metals. And the steel wool's corroding. Here's the same situation with the simple addition of an external connection between the two metals. Now, the magnesium's acting as an anode, and it's corroding a little bit. The steel wool's acting as a cathode, and it's not corroding. It's the same situation with something like a galvanized screw or a galvanized nail, only in that case, the electrolyte is the moisture in the air, and the electrical connection between the two metals is the fact that the zinc is coated right on top of the steel. But any breaks in that coating will be protected by the exposed steel underneath acting as a cathode, with the coating itself acting as an anode. The magnesium in these coffee pots was actually cut from a much larger rod that was designed to be buried next to underground pipelines. It protects scrapes and breaks in the paint job the same way it's protecting the steel wool in this example. In industry, it's called cathodic protection, and it's used on railways, pipelines, and ships. Not that one, I guess. Actually, I've just invented cathodic protection for cars. There's one little catch. You have to cover your entire car in moist dirt. Think it'll catch on?
Stay tuned for part 3 of The Dam Busters, starring Michael Redgrave and Richard Todd, next on Magic Shadows.
Once you've seen the success stories outlined in Frontrunners, you'll want to watch a special on how to start your own business. A studio discussion featuring the entrepreneurs from the series and small business experts exploring the options, including starting from scratch, buying an existing business, and franchising. How to Start Your Own Business, a summary, Thursday at 8 on Frontrunners.
Hello, I'm Bruce Rogers for Money's Worth, a series about your money and how to manage it.
And I'm Cynthia Wine. Continuing our annual income tax series this week, I'll be looking at deductions for students of all ages.
We'll be examining how our play-the-market portfolios have affected our 1985 taxes.
And Brian Costello will be here to explain claiming income on Canada savings bonds.
We'll give you the time, date, and number for our annual income tax phone-in hotline, so join us, please, for your Money's Worth.
Friday at 8 and 11 and Monday at noon on TV Ontario.